This is my presentation on fatigue and recovery. Fatigue is the inability to provide the force or power needed to complete the task. It's your body's strategy for communication that you need to reduce the intensity of the activity you are partaking in, and therefore stops you from performing at a level that may cause you harm. In terms of exercise and analysing it for causes of fatigue, there are a few different factors. The type of activity contributes, so whether it's continuous or intermittent, the energy system used, muscle fibers used, for example slow oxidative or fast glycolytic, the type of muscle contraction, the intensity and duration, and finally the individual's level of fitness. There are also 4 main things that can affect how much somebody fatigues during sport, and some of these are the same as before. So the intensity and duration, the fuel or the energy source, but also the neuromuscular factors and waste products. There are also 3 types of physical fatigue, which are local, general, and chronic. Local is localized in the muscles from repeated contractions without recovery. General is post-training or competing and feeling physically weak, whereas chronic is a weakened immune system from excessive overtraining and inadequate recovery. Also, there's psychological fatigue in terms of how much you really want to train and succeed. If you tell yourself you cannot do something, then you won't. So now we'll look at recovery quickly. Recovery is simply the restoration of our body systems to return to homeostasis, so resting levels, to resynthesize our energy systems and energy sources, to repair any damage that has happened to our body as well, so any damage to muscle fibers, for example. You can show recovery on a graph in terms of EPOC, which is excess post-exercise oxygen consumption. And within this, there are 2 different stages. The alactic stage, which is known as the fast stage as well, which restores ATP and PC, and also the lactated stage. This is known for removing waste products, and it's also known as the slow stage. What determines EPOC is our O2 deficit, which is how much of your effort was anaerobic. Now we're going to look at an activity of maximal intensity and short duration. A sporting example of an exercise which is of high intensity and short duration would be a 100-meter sprint. The energy system used in this would be ATP-PC system, and the fuel would be phosphocreatine. And as it has such a short duration, there will be minimal harmful waste products. PC is triggered by the buildup of ADP after all the ATP has been used. The PC high energy bonds break into phosphate and creatine, and this energy is used to attach the phosphate ion to the ADP and make it ATP again, so muscle contractions can continue to happen, therefore meaning the only waste product is creatine, which causes no harm. However, during activities of a short duration but high intensity, the athlete will experience ATP and PC depletion. This is due to the fact that we only have enough PC to last us 10 seconds of maximal exercise before the next fuel needs to be introduced. So therefore, PC levels can be almost totally depleted after maximal exercise, which is stated by Casey et al. In his study in 1996. During these types of activities, fast glycolytic muscle fibers are recruited, and from this data from the study by P.L. Greenhalgh et al., you can see that these muscle fibers have the greatest PC depletion from pre to post exercise in terms of this is the most dramatic change. So therefore the muscles become locally fatigued as they are constantly contracting without a chance to recover. Once an athlete run out of PC, they would either have to lower the intensity of the exercise or stop altogether, as there is no possible way to sustain that level of intensity over any lengthy duration, therefore meaning that performance would drop. However, fatigue can be reduced in this case by a creatine supplementation, and as you can see from the data found by Casey et al., that the black bar, which represents the participants who had the creatine supplementation, were able to perform to a higher level, therefore suggesting that it helps to prevent the depletion of PC, helping to reduce the speed at which fatigue can take place. Recovery is the process of our energy systems being replenished. So in this case, our ATP PC systems was the only system being used, so is the only that needs to be replenished. Therefore, is a fairly high oxygen debt, meaning the epox, alactic or fast stage is going to be larger than the lactic acid stage. So there will also be a fairly large deficit, as most of the activity was anaerobic. The recovery time for an activity of this duration and intensity would be very quick. Our phosphagen stores only take around 3 minutes to recover, and there is a very minimal amount of waste products to remove. We'll now look at activities of moderate intensity and moderate duration. An example of this would be a 400-meter sprint. The lactic acid system is used, so therefore glycogen and glucose are the fuel sources because the activity lasts for more than 10 seconds, so PC runs out. The waste products are lactic acid and carbon dioxide. Lactic acid is harmful and decreases performance and therefore intensity that the performer is able to perform at. The lactic acid system tends to provide ATP for muscle contractions for around 90 seconds before it needs to resynthesize by another energy system. So you will fatigue due to the depletion of glycogen and glucose. When using this system, the athlete will be respiring anaerobically, so the RER value will be over 1 because the carbon dioxide is being produced, more carbon dioxide is being produced than oxygen being used. Lactic acid is produced, and hydrogen ions are the acid in the lactic acid. They cause the burning sensation when you are exercising. On this graph, you can see this is where the lactic acid starts to build up, and OBLA is where it starts to affect someone's performance, and this is around 4 millimoles. The reason that hydrogen ions affect an athlete's performance is because it interferes with the electrical impulses in your muscles, therefore slowing down reactions and muscle contractions. Two other processes known as acidosis and alkalosis take place when the lactic acid system is in use. Hence the name acidosis. This is the blood having an increased acidity, and it can occur due to an increase of metabolic acid, lactic acid in this case. Alkalosis is the reduction of hydrogen ion concentration in our blood's plasma, and it's caused by hyperventilation resulting in a loss of carbon dioxide. A study was conducted by Karins in 2006, which showed how exercise and isolating muscles shows that acidosis has little impact or may even improve performance in high intensity exercise. However, alkalosis can improve performance when competing for 1 to 10 minutes. So Karen said that although acidosis has little effect when it is severe, it can impair performance as it reduces central nervous system impulses and drives for our muscles. The removal of lactic acid is reliant on our body's buffering capacity, and this decreases the effect that lactic acid has on the body, therefore decreasing its effect on performance. A way some athletes try to improve this is by soda loading. We have hydrogen carbonate ions in our blood which absorb the lactate from the acid, converts it into carbonic acid, which can then be removed from the body via the lungs by soda loading. This increases and improves an athlete's buffering capacity, and this then removes more lactic acid at a greater rate. As you can see from the graph, after 8 weeks of training, the group that soda loaded had improved much more. The recovery time from an activity of this intensity and duration would be fairly long for the lactic acid or slow stage of EPOC, as a large amount of lactic acid is produced, which can take up to an hour or even longer for the O2 deficit to be replenished and for all the waste products to be removed, as you can see from this graph. The alactic stage will take slightly longer for this activity as it has to replenish ATP-PC stores, which, as I said earlier, takes around 3 minutes. Also, to resaturate myoglobin and hemoglobin, around 0.5 litres of oxygen is needed for 100% recovery, and this takes around 1 to 2 minutes. Lactic acid is used in 4 different ways in order to remove it. 65% of it is used as fuel in the Krebs cycle and ultimately becomes carbon dioxide and water. 5% is converted into glucose, 20% is converted into glycogen, and are then both used in the Cori cycle. And finally, the last 10% just simply becomes protein. The oxygen deficit from an activity like this would be fairly large, as the performance effort would be entirely anaerobic, therefore meaning a large oxygen debt. The lactacid stage on the graph would be very long and stretch over a long period of time, whereas the alactic stage would be much shorter. Activities such as this can lead to what's known as DOMS, which is the delayed onset of muscle stiffness or soreness. This is caused by small-scale damage to our muscle fibers from exercise. Ways to avoid this would be to complete a cool down after the activity by starting with a light jog and then doing some static stretches to help with the process of removing the waste products. We'll now look at submaximal intensity and hydration activities. So a sporting example of this would be a marathon. The aerobic system would be used for an activity such as this, and then in this glycogen is used as a fuel, but also oxygen and protein are used as fuels because protein is used in activities of aerobic respiration. When these glycogen stores become depleted due to reduced rates of carbohydrate oxidation, athletes can experience hypoglycemia due to blood glucose levels being low. This is a feeling of extreme fatigue, and in extreme cases an athlete may even collapse. The main waste products produced are carbon dioxide and water, so neither are too harmful and therefore do not affect the performance. But some lactic acid is produced as the duration goes on, and also sometimes intensity may slightly increase. So this will decrease the athlete's performance. This system, however, is the most sustainable and lasts for the longest amount of time before an athlete hits the wall. This is when fatigue hits, which essentially is again the depletion of glycogen, protein, and oxygen levels in the blood. Glucose is also a key substrate for the brain, so low blood glucose levels can contribute to central fatigue due to a lack of glucose in the brain and therefore slowing down all processes due to the fact that the brain is our key communicator. In exercise that is of a longer duration, there are some neuromuscular factors that can also contribute to fatigue. One is calcium depletion. Calcium is required for muscle contractions, and it can leak out of the sarcoplasmic reticulum, therefore depleting the amount of calcium that is available for muscle contractions, therefore weakening them. Nerve impulses are also affected due to the buildup of hydrogen ions. They cause an increase of acidity, which slows down impulse transmission, therefore reducing force that we can produce via muscle contractions. Further neuromuscular factor is the depletion of ACH and chlorinterase. ACH is needed for muscle contractions to be produced as it transfers the impulse across our synapses. A chlorinterase is the enzyme that breaks down ACH after it has been used in order for it to complete this function again. Without a sufficient amount of ACH, muscle contractions cannot occur and fatigue will set in. The strategy to help prevent fatigue in activities of this intensity and duration is carbo loading. This can be done by, in the days leading up to an event, consuming large amounts of carbohydrate, and then during an event consuming high sugar energy supplements. As you can see from the graph, after carbo loading, the muscle glycogen of an athlete is much higher. Research conducted by Hawley et al. In 1997 concluded that carbo loading can improve endurance exercise performance in events lasting longer than 90 minutes. Recovery for this activity could take anywhere from hours to days. The oxygen deficit in a marathon would be fairly small to begin with, as we would be respiring aerobically, therefore using enough oxygen than there is carbon dioxide being produced. The two stages of recovery, the alactic and lactacid stages, may not take as long due to the fact that there has been mostly aerobic respiration, meaning there is very little lactic acid. The alactic stage may take a bit longer though, as more stores will need replenishing. Restoration of the muscle's glycogen is the part that takes the longest, and this can take days to recover. After exercise of this duration, our body has some metabolic needs, which are the extra VO2 that needs to be consumed by organs and muscles such as your heart and respiratory muscles. This is needed in order to sustain heart rate and stroke volume, and also breathing rate and tidal volume. An active cool down would help in the recovery process in order to avoid DOMS again. This is because our skeletal muscles continue to work as a pump to keep the blood circulating around the body, and therefore speed up the removal of waste products that may cause harm, such as lactic acid. That's my presentation on fatigue and recovery.